In this video, I want to introduce another type of contrast enhancement. It's called nonlinear contrast enhancement. And this is a category. And histogram equalization is a very fundamental nonlinear contrast enhancement. So the purpose of histogram equalization is to assign approximately, not exactly, okay, an equal number of pixels to each of the user-specified output grayscale classes. It could be 8 classes, 32, 64, and maybe 256, but it depends on the number of bits in your image, okay? If it is a 3 bits image and each bit is a binary value, which means there are 2 to the power of 3, which is 8 possible values in your image, right? Then there should be 8 grayscale classes. If it is a 4 bits image, 2 to the power of 4 is what? Is 16, which means that there could be 16 possible grayscale classes. Okay, so here is an example. This is a original histogram. Okay, how many classes do we have? 1, 2, 3, 4, 5, 6, 7, 8. So 8 classes from 0 to 7, which means this image is a 3-bit image. 2 to the power of 3 is 8. 8 possible classes from 0 to 7. And the vertical axis, of course, is frequency because it's histogram, right? And you can say this histogram is highly skewed because there is a long tail on the right, which means that some category, for example, category of 1, has a lot of pixels within, more than 1,000. But how about category 7? Category 7 only has 81 pixels. Okay, so that's the reason why we have this highly skewed histogram. We don't want that. Okay, we don't want that. What we want is like this. This is a histogram of the same image after the histogram equalization. And here you can say that compared to the original histogram, the difference in terms of number of pixels in each category is smaller than the original one. Although it could still be very large. For example, for category 3, there are more than 1,000 pixels. For category 7, still 448, but it's much better than the original histogram. And we can also say that some categories, they do not have any pixels within category 2 and category 4. Okay, so if you compare these two histograms, the right one is the one that has been equalized. Okay, if you ask me what's the difference in terms of the specific image, I do not have examples here in our slides, but you can simply Google image histogram equalization. There are a lot of examples online showing you the original image and the image after histogram equalization. You will find out that the one after the image after the histogram equalization is brighter, and all those pixels, there are bright pixels, there are dark pixels, and the dynamic range again is larger. I would not say dynamic range. Pixels, they are, I mean, the tone of the image has been expanded. Okay, before the histogram equalization, the image could be very bright or very dark. But after the equalization, there are dark pixels, there are bright pixels, so the image looks better. So it's a type of enhancement. Okay, let me show you how to do this. Okay, so here we only have a red arrow, but what happened within this red arrow to transfer original histogram to this equalized histogram? Here is how you do it. So here is the original histogram, right? So there are 7 non-zero brightness values in this image from 1 to 7. Let's just call it a category. simply call it class 1, class 2, until class 7. Of course, we also have a class 0, okay? And let's just assume this image is a square one. It has 64 columns, 64 rows. So totally there are 4,096 pixels in this image. So here is a table showing you details according to this original histogram. So original brightness value BVI. So for value 0, we have 790 pixels. This is what the first Peter is trying to tell you, okay, in this histogram. In class 0, there are 790 pixels. So etc., class 1, class 2, until class 7, and their frequencies here. Okay, so the next row here is called Li. Li is the ratio between brightness value and 7. So n here is 7. Is the number of non-zero brightness values. We have 7 non-zero values, right? So for the first category, for the first class, of course, the ratio is 0 because the brightness value here is 0. But in the second class, the ratio between 1 and 7 is this value. The ratio between 2 and 7 is this value, etc., etc. Okay, for all classes. This row here is special. It's something called cumulative frequency. Okay, so it's still a ratio. The ratio, and for this ratio, the denominator is the total number of pixels in this image, which is the same, 4,096 for all categories, right? So the numerator is different. The numerator is the cumulative number of pixels from 0 to 7. For a category for class 1, it's simply 790. That's the cumulative so far because there is only one class. But for class 1, we need to add frequencies of class 0 and class 1 to calculate the cumulative frequency and divide that cumulative frequency, which is 1,813 by total pixels, by the number of total of all pixels. So we get a value of 0.44. And we do this again and again for all 8 classes. We have cumulative frequency from 0.19 to 0.44 to something until 1.0. Because it's cumulative, so for the last class, numerator and denominator are the same, which is the total number of pixels in this image. So the ratio is 1.0. So far, so good, right? So let's just use another histogram or another figure, another chart to show the content in this red rectangle. So this is transformation function. So here we have brightness values, okay, from 0 to 1 to 2 to 7. And here is actually from 0 to 1/7, 2/7 until 1. Okay, this is a ratio, not the original exact brightness value. Okay, but here the vertical axis here is called Ki. Is this, right? Cumulative frequency from 0.19 to 0.44, 0.65 until 1. Okay, so now we need to project original brightness value BV to a new value after the equalization. So this is a key part of histogram equalization. Originally, it was 0. So what's the new BV value after the histogram equalization? How to calculate that? We do this. We use the cumulative frequency of that class, multiply 8 minus 1. 8 is the possible class numbers for this image, which is 8, right? 2, to the power of 3. This is a 3-bit image, and which is 8. 8 minus 1 is 7. Of course, if it is 4-bit image, 2 to the power of 4 is 16. 16 minus 1 is 15. So you should not multiply 7. You should multiply 15 instead. But here, let's stay with this image. It's a 3-bit image. So 2 to the power of 3 is 8. 8 minus 1 is 7. So 0.19 multiply 7 is 1.33. What is the closest integer to this value? Is it 2 or 1? Of course, it's 1. So we assign 1 as the new value for class 0 in the input image. So 0 has been projected to 1. Okay, which means all those pixels have a value of 0 in the original image. They have a value of 1 in the output image after the equalization. Get that? Let's do this again. So how about the next brightness value? Originally, it should be 1. This pixels, 1023 pixels, they had a value of 1 in the original image. What's the new value for these pixels? You multiply 0.44 by 7, which is 3.08. What is the closest integer to 3.08? 3 or 4? Of course, 3. Then these pixels, they have a new value of 3 after the equalization. And we do this repeatedly. Okay, use each cumulative frequency to multiply 7 and get a specific value and find the closest integer to that value and assign that integer as the new value of pixels in that class. So 0 is projected to 1, 1 is projected to 3, 2 is projected to 5, 3 and 4, they are both projected to 6. Because the calculation result, 5.67, 6 is the closest integer. 6.27, 6.23, 6 is also the closest one integer, right? So 3 and 4, they are, both of them are projected to 6. Similarly, we do this for class 5, class 6, class 7. They are all in class 7 in the output image. Okay, next, let's redraw the histogram. So same table here, right? So in the new image, class 1 has 790 pixels. Class 3 has this value of pixels. Class 5 has this number of pixels. Class 6, how about class 6? Class 6 has a number of pixels of this. So you need to make sure that this 656 pixels and 329 pixels, they are all having a value of 6. Similarly for 7, in the new image, class 7 actually covers 3 original classes. All these pixels in original 3 classes, they are now in 1 class, class 7. They all have a value of 7 right now. So there is no class 2, there is no class 4, there is no class 0 in the new image. How about them? Simply 0 pixels, okay? So this is the result. This is the equalized histogram I showed you 2 slides before, right? So there is no pixel for class 0, no pixel for class 2, no pixel for class 4. For class 1, okay, so this is in the new image. For class 1, there are 790 pixels. Okay, similarly for class 3, class 5, class 6 has how many? 985 pixels, which is the sum of 656 and 329. Okay, similarly for 7, This 448 result is the sum of the three values. Okay, so that's histogram equalization. Okay, if I get back to this slide, this is what you do. Okay, from original histogram to equalized histogram, you need to finish this table. The most important part is cumulative frequency, and you use this calculation to decide new value for all pixels. Okay, and then you use new values to redraw the histogram. Okay, okay. In this lecture, in the first half of this lecture, because lecture 7 has 2 weeks, right? So for the first week of lecture 7, the last part of the first half is this. Another nonlinear contrast enhanced method is called logarithmic contrast stretch. So we have a linear contrast stretch, right? We have a piecewise linear contrast stretch. In piecewise method, we use 2, 3, or even more linear functions to stretch the whole image. And logarithmic stretch here is very similar to piecewise, but in piecewise we use 3 linear functions. And here, because logarithmic is a nonlinear function, you can say this is a curve. This is not a straight line. So logarithmic function is a nonlinear function. And you can say for the first half of logarithmic function, the image has been enhanced because, let me draw this in general, because for again, BV in is for is along the horizontal axis, BV out is for the output image, right? So for the first half of logarithmic, this is the range, right? This is the range. So actually, this part is the range for input image, for original image. For output image, the range changed. It's from here to here. So this is output range. This is the output. For obviously, the first half of logarithmic function enhanced these pixels within this red range because they have a larger, these pixels, they have a larger range in terms of their values in output image because the length of this green part is longer than the length of this red part, right? Right. So how about the second half of logarithmic function or logarithmic contrast stretch? Compression, because if you do something like this, right, you find out the input range and output range for the rest pixels in this image. The second half of logarithmic function actually compress them. Okay, and besides logarithmic, we have another mathematical function. Is called what? Inverse log. Inverse log. Let me erase all these drawings. Inverse log is, you can consider this as a mirror image of logarithmic by this linear function here, by this x equals y linear function. So for inverse log function, the first half is going to compress the image, okay, and the second half is going to enhance the image. So you can consider a logarithmic function a combination of 2 segments. The first segment is this, okay. If you are going to use a linear function to approximate logarithmic function. So this is the first segment, and this is the second segment. If you are going to use two linear functions to approximate logarithmic function, okay? But here, logarithmic function is one function. That's the reason why we call it a nonlinear function, because if you're going to use a geometric feature to address it, it's a curve instead of a straight line. And similarly, if you want to use two segments, two straight lines to approximate an inverse log function, this is the first segment, and this is the second segment. But again, just like logarithmic function, inverse log function is a curve. It's one function instead of two straight line linear functions representing these two blue segments. So logarithmic contrast stretch is very similar to piecewise stretch, which is a part of linear contrast enhancement. Okay, it's a little bit complex. Okay, you may need some time to figure out what's going on here, and I would suggest reading the book, okay, and find out when you're trying to figure out if the image has been enhanced or compressed. Find out the input range and the output range. If the output range is wider, is longer than the input range, then the image has been enhanced, or all those pixels in this image, they are enhanced. If for other pixels, their input range is longer or is wider than their output range, then you know that it was not an enhancement, it was a compression. Okay, that's all I want to introduce for the first week of lecture 7. Okay, I will see you in the next video for the second half of this lecture. Thank you.